Hi folks, my name is Jeff Inman. I am a software developer at Los Alamos. I'm going to talk about object storage over RDMA. Actually, I'm going to spend most of the time talking about systems on top of object store, and RDMA stuff is new work. I'll get to that at the end. So new that we don't actually have very meaningful performance numbers to show you, but I can do it if you find the concept interesting. So a typical storage hierarchy in a supercomputer data center has the memory, parallel file system, and the supercomputer has to stop every now and then to write checkpoints out to storage. So the size of the memory, our new Trinity machine has 2 petabytes. If you want to keep the machine busy 90% of the time, that implies a certain minimum bandwidth for writing checkpoints. However, expanding the bandwidth of the parallel file system implies that you're buying enterprise disks, expensive hardware, and so forth. So there are some cost problems with growing the parallel file system to match the size of the machines that we have. And then similarly, there's an issue with archive, expanding the bandwidth there. Tape archive, that would be, implies buying tape drives, lots of tape drives and robotics, and those are expensive. So scaling bandwidth in our storage hierarchy was a challenge, and the solution is to add more layers, of course. So we've added a burst buffer between memory and parallel file system. That's a bunch of flash. The idea is that you can offload the checkpoint from the machines a little faster and get the machine back to work again, and then pick maybe 1 out of n of the burst buffer writes off to parallel file system. Similarly, we've added a layer between the PFS and the archive, which we call campaign storage. Excuse me. The name campaign storage refers to the lifespan of a compute project. We call those campaigns. So campaign might last a couple of years. And the goal is that the campaign storage would be a place where we can move data off the parallel file system and keep it for long enough that people don't have to shuffle it off to tape. So it's a campaign storage, and the goals for it are high capacity, reasonable bandwidth. The big POSIX, as I was mentioning, can be expensive because you're buying high-end disks and servers. And big POSIX also implies some guarantees that we don't actually need that much. We don't have a bunch of writers all potentially writing to the same file, or if we do, they're well-behaved parallel applications that know how to write without stepping on each other's toes. So what we need are files and directories, the usual access control that everybody's familiar with. We want it cheap, we want it resilient, we want it high capacity and bandwidth, and we have some special metadata needs. With the size of memory on these machines, we won't be surprised to see petabyte-size files before long, and or trillions of tiny files, billions of files in a directory. So all of those are not far away, and we're willing to trade away things like random write access and update in place. We don't actually need those things for our storage hierarchy. Here is a sort of a picture of the tiers with some sketched in bandwidths and capacities. The outlier there is campaign storage, but that's just showing sort of the initial configuration. Those change columns kind of show the gradations in steps between the layers. So we start campaign with the goal was something like 30 gigabytes a second, but that should grow to hundreds of gigabytes a second, and the 30 petabytes of capacity will grow to hundreds of petabytes, assuming this all works. And then tape is just tape anymore. So people don't use tape to store stuff that they don't have room for on the parallel file system. It's really stuff that you need to keep forever. Some people think maybe the layers coalesce again over time and we end up with a bandwidth tier and a capacity tier, sort of with campaign and burst buffer spreading into their surrounding layers maybe. Okay, and so our implementation of the campaign storage is called MarFS. Mar, Spanish for ocean. The idea is it's a data lake that's so big it's an ocean. So you need MarFS. And there are the two yellow blobs at the top there are the two ways that users interact with it. So Fuse is for interactive access. We intend that to be metadata curation, things like that, chmod, move, RM, and so forth, but not really big data movement. The big data movement's handled with pftool, parallel file tool. All these are open source. You can find them on GitHub. So pftool and MarFS are there. And so the idea is people would use pftool to do the big data movement. We split the internal implementation into separate areas. So metadata, the default implementation of metadata is just a GPFS file system. So files and directories and all the chown and chmod just works. However, the files are actually just sparse files. They're truncated to size, but they have X adders that are object IDs pointing off into the data repository, which is by default an object store, a commodity object store, and the cost effectiveness there is that we can use cheap disks in the object store, and we get our resilience through erasure coding that's provided by the object store system. Okay, and since object stores typically have a ideal object size maximum, and also because we want to write big files in parallel, we impose a maximum size object, and then files that are bigger than that get broken up into what we call a multifile. Excuse me, a multifile. So many objects representing a single file transparently to the user. We also have a packed file, so many small files might be stored in a single object, again, transparently to the user. And then at the end of all these, we invisibly write some recovery info that would let us rebuild the metadata somewhat should there be a catastrophic failure in the metadata file system. Very unlikely, but we've got the belt and suspenders approach there. The implementations are modular also, so the metadata implementation is sort of a functional interface, bunch of functions that perform metadata operations for MarFS. We call these abstraction layers, so there's a metadata abstraction layer, or MDAL, and a data abstraction layer, or DAL. So the metadata implementation has, setxadder and makedir and opendir, things like that. You could write a drop-in replacement by just implementing all those functions and tweaking the config a little, as I'll show you. And then similarly with the data abstraction layer, you could write your own REST-ful implementations of put, get, delete, and a few more, and have a drop-in replacement for that. And so I'll show you about some experiments we've done with those in a moment. Here's what the config file looks like, just XML file on the right there. I'll show you some of the namespaces and repositories in a minute. So the config file shows a top-level mount point there /campaign. So all the namespaces would fall under that, and then namespaces represent a metadata, basically a subdirectory. You could think of it, but they can have independent implementations. Here's what a namespace and repository spec look like. On the left there is a namespace /project1, so that would come under /campaign/project1, and everything under there would be controlled by this particular namespace. I don't know if you can see, I have a laser pointer. Let's see, I've heard people mention it's on the left. Okay, I'm not getting that. Okay, if you look at the names, oh, sorry. I thought I saw that. Okay, it says on. Oh, now it says on. Okay, there you go. So you have two sets of permissions here, iperms and bperms, that's interactive permissions and batch permissions. The idea is that the interactive permissions apply to Fuse, so you can control the interactive implementation, interactive access distinctly from the batch access. And the point is that admins, well actually first let me enumerate these. So you have read meta, write data, write data, truncate data, unlink data. And the idea is an admin might want to remove the write data from the Fuse access, so we don't have people trying to jam a petabyte through Fuse on the interactive servers. And then batch is likely to just be wide open like that. And then they both refer to a repo that I'll get to in a second. And then there's some spec down here of the where in the file system the actual metadata is kept for that particular namespace. Okay, and then the repo, interesting thing to note there is just a description of the host. There's a bunch of servers that are the object store, in this case 12 servers. And there's the chunk size that says how big an object can be. Anything bigger than that gets broken up into multiple objects. Okay, and so here's a picture of the way this thing would be deployed. We have some interactive servers, FTAs, file transfer agents. So people would, oh look, I have a mouse. People would log into the FTAs there, and they could do their metadata interaction, their curation, that is through the interactive agents. And then if they want to launch a parallel big job to move data, that would get spawned off onto the batch FTAs. There's metadata servers, GPFS servers would be there, and then a bunch of object storage servers. And that network is EDR, Infiniband in our production, and it's FDR on our little test bed. Okay, so object stores, the object servers, all of them volunteer to provide any object, and so we just pick one of them at random. So we have pftool running across a bunch of batch nodes, and each task can pick object storage servers. So this is doing a big data movement from, say, Lustre to Campaign, and then internally the object stores route the request to wherever it's stored. And so here I'm showing how we wrap the get and put semantics of the object store inside a file, sort of a more familiar open write, close type interface. So on the left you have an open, somebody calls MarFS open one of our apps, and create a file handle with some locks in it, and start a put stream off to the object store. That's a libcurl put operation basically, and there's a callback to a read function that blocks waiting on a lock in the file handle. We actually defer that put stream creation until the first write anymore, but this was the original way it worked. So a write then comes along. You see the mouse? Yeah, a write comes along. And it has a buffer that somebody wants to write. Basically, we unblock the libcurl callback function, which then can transfer data out of the buffer into the put stream, and then blocks again when the buffer is exhausted and the write gets to return. So that is a use of the data abstraction layer object store implementation. So we did an experiment with an MDAL to see about scaling metadata. The goal here was to do a scaling experiment. So we're not actually, the goal isn't to create persistent metadata. So we used tempfs, not cheating in this case because the goal is really just to look at scalability. So we make that very cheap operation so that we would reveal any scaling issues. And it scaled very well, 140,000 cores of Cielo before it was decommissioned. We got close to 1 trillion files in a single directory, something like 1 billion file creates per second, less than that, something like that. Scaled very well. But we wanted to replace the object store. It didn't seem to be performing quite the way we hoped, so came up with this scheme for a multi-component repository where we're basically doing our own object store. Each of these columns here you could think of as a rack. It's got a storage node server basically and some JBODs that have ZFS zpools implemented, 17+3 in the production implementation. And in this case, there's 12 of them. So we do our own erasure coding on top of this. So we take a object that's going to be written and break it up into 10, then generate 2 parity blocks as well. So we have a 10+2 that we're writing out to these 12 servers. If you call this thing a pod, in production, we have 4 pods. So 48 servers. Pick your pod by hash, do the erasure coding, and write the stripe out to the, and pick your zpool by hash as well. So here's how this spec for multi-component looks. We do the erasure coding with Intel's ISAL library. It's very efficient. And so with 48 servers and 4 zpools each, we have 48 plus 4 NFS mounts on each node that's going to be talking to this storage system. And so part of the spec there is the path that the NFS mount looks like. It's a pattern because as our code is accessing this thing, we're going to fill in the pod with a hash, and we're going to fill in the block. That's which of the 12 any specific block's going to. The capacity then gets filled in with which zpool we've picked, and then underneath that is also a scatter directory internal to the zpool that lets us reduce the number of internal object files that might be found in any directory. Here's the 10+2 in the spec, and this actually must be from the test bed since there's only 1 capacity and 1 pod. Okay. So now we get to RDMA. This is sort of a new, very new thing I've been working on recently to replace NFS with a custom client server over RDMA. So the idea is we'll get rid of the NFS overhead. We'll have RDMA bandwidth. We're actually, in this case, we don't care so much about latency. We're all about bandwidth. But we want that bandwidth. So everything else is pretty much the same. The ISAL, we still use that. We still write stripes across the independent servers, but instead of using NFS to get to them, we now just use this custom client server model, and showing the get and put implementation, and we get to build it ourselves from scratch. So there's it's written in terms of opens and writes and close, etc. You can see in this case there's two agents. One of them is reading from a file, one's writing to a file. So this could be the client of a put, and this would be the server side of a put. Or this could be the server side of a get, and this is the client side of a get. Either way, oh, I should have mentioned we're using R sockets. That seemed like a sort of a design win to me. Apparently no big losses in performance, and a lot easier to get going quickly. So I thought it turned out that way. The idea is at open time, then the read side does a mapping of a buffer and transmits that to the writer. REO offset is the RSockets term, but it's just basically mapping a buffer for RDMA. And then because the RDMAs are transparent, there's a little bit of protocol around each write. So the reader has to send an ACK saying the buffer is ready for more writes, and then the, then the writer does the RDMA and then sends a data message saying here's how much data you got, and wash, rinse, repeat until that's finished, and then there's a close, a little bit of close semantics. A little bit of extra fur on it because we allow seeks on a get stream and fsync on a put. So where the writer is waiting for an ACK, it may actually get a seek instead. And because the write interface doesn't know anything about the surrounding file moving operation, we just gloss that by setting a marker in the file handle and throwing an error, and then the outer loop can figure out that a seek happened and go do the seek and pick it back up again. And similarly for fsync on the read side. So as I mentioned, I don't have really meaningful numbers about the RDMA. We have a test bed that's similar to production, a little bit weaker hardware, only 6 servers instead of 48. So our 10+2 stripes go around twice, and so 2 Z pools on each one. We're using all SMR disks everywhere, all shingled disks. So I think we're disk limited on the test bed. The NFS and RDMA are performing about similarly. You can see the NFS on writes gets, I don't even show read because nobody reads from an archive. We just write to it. Just kidding. So we get about 2.3 gigabytes a second, but over time that trails off after you start to saturate the PMR cache on the SMR drives, and it looks like NFS might be partly to blame for that, since NFS does lots of random writes at different locations, or seemingly random. So that's even harder on the SMR drives. However, we lost one of the JBODs on the test bed, so I haven't been able to assure myself that that doesn't happen with RDMA, although for several terabytes of writes, I wasn't seeing that, and it does show up that quickly for NFS. However, no promises there. We may have a similar issue with RDMA. When you go look at production, we have not had a chance to test the RDMA interface there yet. The object store we were hoping would get 30 gigabytes a second, and that was more like 20. NFS around 12 for writes, 22 for reads. There are some tricks that have been suggested that might work for boosting the NFS performance. And then RDMA, like I said, I don't have numbers yet. Theoretical bandwidth, when you look at the drives and the controllers and the network and all that, should be more like 50 to 80 gigabytes a second. So high hopes for that space. Lots of people have worked on the project over time. Here are a bunch of them. And thank you. Any questions? And go easy on the RDMA questions, please.
Shucks. Did you try NFS over RDMA?
Yes, actually. Yeah, I
And you
believe that
decided
is.
to write your own instead?
I'm sorry?
And you decided to write your own RDMA instead?
Yeah, the performance we're seeing with the NFS over RDMA was still not what we had hoped. So true, you're getting better bandwidth through NFS, but you still have at the NFSD side, you still have the breakup of writes into lots of small things that NFSD seems to pick its own, it's got a bunch of threads and each thread decides where it wants to write. And so maybe that's part of the issue.
You created your own object store. Did you look at Ceph, Rados, any of that?
We looked at all those. I can't personally speak for exactly all the decisions that were made, but I think it was decided that they weren't quite ready for prime time for our specific needs. I know some people felt they're plenty ready, but I think we didn't feel they were quite ready. And there's also the sysadmin issue with object stores in general. It makes them nervous to have all their data stored in some system they don't understand. Not that they aren't very smart, capable people, but the data is hidden in the object store. You're dependent on the storage implementation providers to know where the data is, and I think they feel a lot more comfortable with ZFS, local ZFS pools.
Hi. Which NFS servers were you using? Just the Solaris ones for ZFS, or did you use something else?
We're using Linux NFS. We've tried v4 and v3 both. I'm not sure if I'm answering your question the way.
Yeah, that answers it. So which kernel versions or distributions, that kind of information?
I don't know. Do you happen to know, Susan, what the TOS is?
They were probably 6.x, Red Hat 6.
Yeah, 6 definitely.
Did you
It
have?
might have been 7. I don't know if they went to TOS 3 or not.
Yeah,
Okay.
that might explain some of your performance problems. Have you
Okay.
tried any newer ones?
I think the sysadmins have given it a pretty good effort. They have some constraints on just picking an arbitrary OS because our data centers kind of standardize, and we're usually several years behind on the latest system, mostly because people have worked out, that they trust this one.
If you had PNFS on RDMA, would that be more interesting, more compelling for you?
NFS on RDMA?
PNFS.
Oh, PNFS. Sorry, I don't even know what that is.
Okay, well, I'll talk about that in about 90 minutes.
Okay. Okay. Parallel NFS, I'm guessing.
Thank you.
Thank you.